Alright, here we're going to be talking about right angles, perpendicular lines, and how perpendicular lines relate to transversals. So our first definition here is the definition of a right angle. An angle is a right angle if and only if it has a measure of 90 degrees. So that's the definition. It's a biconditional statement, which means it goes both directions. If I say that something's a right angle, I know that it has a measure of 90 degrees, and vice versa. If it has a measure of 90 degrees, I know that it can be called a right angle. The definition of perpendicular lines really just directly follows from that. Two lines are perpendicular if and only if they intersect at a right angle. So if two lines intersect at a right angle, I can call them perpendicular. That's just how we talk about perpendicular lines and right angles. So it might seem like these are very intuitive and common sense, and you don't need to say these, but they do need to be explicitly stated sometimes in proofs. Really specifically, I think the right angle one is the one that gives people more trouble, just because you know that a right angle is 90 degrees, but saying the number 90 degrees requires that definition. If you say that something's a right angle, it doesn't imply that number until you state that the reason is that it's the definition of a right angle, that we can call it a right angle because it's 90 degrees. All right, so we're going to try a couple proofs here. G is perpendicular to E, so I'm going to mark that on here. G and E are perpendicular, so they meet at a right angle. And 10 is a right angle, which is also marked on there. We're going to prove that E and F are parallel. So first off, I want to just say, actually I'm going to talk about angle 1 since that's the one that's labeled there. Angle 1 is a right angle. So I can say that by the definition of perpendicular lines. I know that they're perpendicular. That allows me to say that this is a right angle. Actually, it allows me to say that all four of these are right angles by the definition of perpendicular lines. All right. Now, by the definition of a right angle, I can say that angle 1 equals 90 degrees. I know it's called a right angle. By the definition, I'm allowed to say that it actually is 90 degrees. Kind of the same thing for angle 10. Actually, it's exactly the same thing by the definition of a right angle. I know that angle 10 is a 90 degree angle also. And then you can see this as substitution of the transitive property. I kind of see this as substitution. We know that angle 1 is equal to 90. So in place of that 90 degrees, I can put angle 1. Angle 10 is congruent to angle 1 because they have the same measure. That is the substitution property. And if I know that angle 10 and 1 are congruent, this angle is congruent to this angle. Then I know that those two lines are parallel because those are alternate interior angles that are congruent. So I could say that E is parallel to F by the converse of the alternate interior angles theorem. And that might seem like way too many steps because once we know that this is a right angle and this is a right angle, it seems really simple that obviously those two lines are going to be parallel. These are the same angle. So we do have alternate interior angles. Probably you're thinking we had it before that fifth step, but we do need to explicitly get into this substitution step. To get to that, we need to say that these are going to be the same number. In another math class, you might learn about different theorems. We don't, there's actually a theorem that says all right angles are congruent. We're not going to learn about this and that in this class, so you're not going to be able to use that. Different geometry classes might work different ways, but it's really whatever tools are available to us in this class. All right, number 2 says that 7 and 8 are supplementary. That and that are supplementary to each other. G and E are perpendicular, which is actually already marked there. We want to show that angle 11 is 90 degrees. So 7 and 8 being supplementary, those are consecutive exterior angles. That's going to tell us right away that these two lines are parallel. I'm not sure if we need that. We're trying to get to 11 being a 90 degree angle. Well, if these are parallel, these two lines, then we could show that these alternate exterior angles are going to be the same. And if they're the same, and we already know that angle 6 is a 90-degree angle, then we can show that angle 11 is a 90-degree angle. So I kind of just outlined it, but I'm going to go through each of those steps. Angles 7 and 8 being supplementary shows that E and F are parallel by the converse of the consecutive exterior angles theorem. If we know that those are parallel, then we can say that 6 and 11 are congruent because they're alternate exterior angles. And we have to somehow associate a number with angle 11. So first, let's think about how we can describe this angle. Well, we know that those lines are perpendicular, so we can say angle 6 is a right angle. It's supposed to say a right angle. Sorry, let me try that again. A right angle by the definition of perpendicular lines. We established that they were perpendicular, so now we're allowed to call this a right angle. And since it's called a right angle, we're allowed to say that it equals 90 degrees. That's by the definition of a right angle. And if 6 equals 90, and 6 equals 11, then 90 degrees is equal to 11. I'm actually going to flip that just so it looks exactly like the statement I want to prove. Technically, I guess we're using the symmetric property there, but I'm not going to be a stickler about that. 90 is getting substituted in place of that 6 there, so 11, the angle 11 does equal 90 degrees. That is just by substitution. We're going to learn about two theorems that really just relate a perpendicular transversal to the parallel line. So if a line is perpendicular to one of two parallel lines, so if I have these parallel lines and I know that A is perpendicular to E, then E is also perpendicular to C. The order doesn't matter. You could say C is perpendicular to E. That relationship is commutative. If it's perpendicular to one of them, it's going to be perpendicular to the other of the parallel lines. That's called the perpendicular transversal theorem. The second one sounds very similar. The lines perpendicular to a transversal theorem is if a transversal is perpendicular to two lines. So we're starting off with now this information. It's perpendicular to both of them. A is perpendicular to E, C is also perpendicular to E. Then those two lines have to be parallel. We can conclude that A and C are parallel. So they're pretty similar. Really, you just always use the given information there. You're starting with a set of perpendicular lines and a set of parallel. Here you're starting with two sets of perpendicular lines and concluding that we have parallel lines. Which actually looks exactly like what we have there. We have two sets of perpendicular lines. G is perpendicular to E, and G is perpendicular to F. So using that last one that we just did, the lines perpendicular to transversal we can say that E is parallel to F. We know it's perpendicular to both, so it has to be parallel. So those two lines have to be parallel to each other. If those two lines are parallel to each other, then we could say that angle 8 and angle 7 are supplementary. Because those are consecutive exterior angles. And if they're supplementary, then they add up to 180. Angle 7 plus angle 8 equals 180 by the definition of supplementary. If you call angles supplementary, then you're allowed to put them into an equation where they add up to 180 degrees. So that's using the lines perpendicular to a transversal theorem. The next one, we're starting with a whole bunch of perpendicular lines. L is perpendicular to P, L is perpendicular to Q, M is perpendicular to Q, and N is perpendicular to Q. And we're told that P is parallel to Q. So we're told all that information. We want to show that these two angles are supplementary. All right, so I'm first going to show that L and N are parallel to each other. So we know that L is perpendicular to Q and N is perpendicular to Q. So L is parallel to N. That's by the lines perpendicular to a transversal theorem. If we know that L and N are parallel, then we know that we have consecutive exterior angles here. 2 and 3 are consecutive exterior angles, and they have to be supplementary. 2 and 3 are supplementary because they're consecutive exterior angles in a set of parallel lines. Well, if 2 and 3 are supplementary, if we can somehow replace this 2 with 1, then we're all set. That's exactly what we're trying to prove. And 2 and 1, we know that they're congruent because they're corresponding angles, and we're already told that P and Q are parallel. So if we have those parallel lines, we could say that 1 is congruent to angle 2 because those are corresponding angles in a set of parallel lines. If 1 is equal to 2, it can be basically substituted in place of this 2. But we don't call that substitution. It feels a lot like substitution. Substitution really only refers to an equation, though. We don't have an equation. We have a statement here. We are placing that 1 in place of the 2. Angle 1 and angle 3 are supplementary. But this is the converse of the congruent supplements theorem. Congruent supplements theorem says that if we have two angles that are supplementary to the same angle, then they're congruent. This is going backwards. We have two angles that are congruent to each other here. Well, then they have to be supplementary to the same angle. That's what this relationship is showing. They're supplementary to the same thing. Whoops, messed that up. All right, let's do one more. A is perpendicular to B. C is perpendicular to B. C is perpendicular to D. We're trying to prove that A is going to be perpendicular to D. First, I'm just going to lay out all of my given statements. A is perpendicular to B. C is perpendicular to B. C is perpendicular to D. Those are given. Using those last two, if C is perpendicular to both of these, I could say that B is parallel to D by the lines perpendicular to a transversal theorem. And now I know that A is perpendicular to B and B is parallel to D. So I could say that A is perpendicular to D by the perpendicular transversal theorem. Remember, that's the one that starts out with a set of perpendicular lines. One of those lines is parallel to another. That's line B. So A has to be perpendicular to D. If it's perpendicular to one of them, it's got to also be perpendicular to the other. All right. Those are all the new ones for today. Try to practice on your own. Ask for help if you need it.